let's see, just that this works. I think this is joint work with Jesko Dojmovic and Elon Yogev. Okay, I'll start. So hopefully everyone here knows what a SNARG is, but I'll talk about it anyways. So we have some language L, some setup algorithm that outputs a CRS. Now the verifier and the prover both know this. The verifier is given some instance X, which the prover claims is in the language. And the prover given a witness generates some proof pi, sends this to the verifier who checks X and the proof, decides whether to accept or reject. And now we want completeness and soundness. If the prover is telling the truth, then the verifier should accept. And if the prover is lying, then the verifier should reject with high probability. And to make this interesting, we also need succinctness. So the prover could just send the original witness W, but we want this to be much, much shorter than the witness. So this makes this non-trivial. And smaller proofs are highly desirable in practice, reduced communication, reduced gas costs, things like that. So in this talk, we're going to be mostly focused on shrinking the proof size as much as possible. So SNARGs come in many flavors, different assumptions like hashes, lattices, pairing-free groups, bilinear groups, some more theoretical things like I/O, publicly verifiable, designated verifier. So I have to say what I'm talking about here. So we're going to care about the smallest practical SNARGs, which are group-based SNARGs. And in this talk, I'm going to specifically focus on publicly verifiable systems, which means that given the CRS and the instance and the proof that the prover sent, everyone can verify the proof. Designated verifier would mean that there's some secret that the verifier gets, and then only this specific verifier with the secret can verify the proof. So the minimal publicly verifiable SNARGs that we have are, well, really from I/O, but if I want any semblance of practicality, then it's bilinear groups. So just to remind people what bilinear groups are, the exact details are not too important for this talk, but I need to go over it a little bit. So we have three groups, G1, G2, and GT, and we have some pairing operation, which takes a G1 element and a G2 element, and gives me a GT element with the exponent being the multiplication of the exponents of the G1 element and the G2 element. And in this talk, we're going to focus on the asymmetric case, where G1 is different from G2. There are also groups where it's symmetric, but they're to get the same level of security as in the asymmetric case, they tend to be much, much longer. And like I said, we're going to focus on getting the most succinct proof systems possible. So we're going to care about the asymmetric case. And what you should have in mind is that G1 is much shorter than G2. So they're really asymmetric also in the size, not just in what exactly they are. And everything I'm going to talk about today is going to be in the generic group model, which means that both my construction and the security analysis is not going to depend on the exact representation of the group. I'm going to kind of treat the group elements as black boxes. They don't have like a bit string representation. I mean, obviously, realistically, they do, but for these analyses, they don't. OK, so what is known? We want to get a minimal proof size. So in this setting, the SNARGs have kept getting smaller and smaller, starting with Groth 10, got 42 group elements. This was improved with a long line of works up to the celebrated Groth 16 work, which gets to 2 G1 elements and 1 G2 element, which is amazing. Obviously, this proof system is used a lot in practice, very efficient. And this is all in the pure GGM. And now, once we also add a random oracle, we can actually improve this, starting with the work from 2 years ago now, I guess, by Helger, getting 3 G1 elements and 1 field element, and then Parry, which gets 2 G1 elements and 2 field elements. And on the impossibility side, so these were all constructions. On the other side, Groth showed in this the same work that there are no SNARGs in the generic group model where all the elements are G1 elements. So this 2G1 plus 1G2 is almost optimal in the sense that you could maybe get 1G1 and 1G2, but you can't get just 2G1 in the GGM. He says nothing about the GGM plus ROM, which is these new works. And also there's some asterisks about what kind of verifiers this limitation works for, but it's basically anything natural. Okay, so what are our results? We show the first 2G1 element SNARG for NP in the GGM plus ROM. Of course, I need this ROM because of Groth's lower bound. I will mention that this is a feasibility result. This shouldn't be considered like practically yet. Hopefully, it can be improved. But so most of the works that I talked about earlier are practical, so it's not exactly apples to apples. And on the limitation side, we show that there's no 1G1 element SNARG for NP in the GGM plus ROM. This strengthens Groth 16 to also add a random oracle, basically. Also, there are some asterisks, so the verify ROM queries are non-adaptive, and we assume that the setup doesn't make any random oracle queries. I will just mention that these things, so any protocol that is kind of built in an interactive setting, which doesn't use the random oracle and then is compiled into a non-interactive SNARG using Fiat-Shamir, will have these properties. In a natural way, at least, will have those properties. So this seems to be a very natural class. OK, just to have a more visual comparison, so Groth showed 2G1 plus 1G2 element in the GGM, so it obviously is also in the ROM. He showed that you can't have 1G1 or 2G1 elements in the pure GGM. Then came these works that improved this in the ROM. And in the GGM plus ROM, we showed that 2G1 elements is possible, 1G1 element is impossible. And just to look at the size comparison of these, Groth 16 has about 1,500 bits of size, where reducing this 1G2 element gets it all the way down to 768. But again, practical work is practically efficient. It's not super far away from being practically efficient, but this should be noted. OK, so I'm going to talk about the result. I'm going to talk, probably I won't have time to talk about the limitations, even though I do have slides. So all about the construction. So the construction is going to follow a very standard recipe of taking a commitment scheme and a PCP and compiling it into a SNARG. So I'm just going to define all these objects and show how I compile them. So to start off with, we have a linear map commitment scheme. So we have a sender and receiver, a setup algorithm which generates some CRS. The sender chooses some vector pi and commits to it, this commitment C. The receiver chooses some query Q. And the sender opens the commitment in this following sense. So it gets some decommitment string D. And alpha, which is supposed to be the inner product between pi and Q. So this is why this is called a linear map commitment. This is actually just an inner product commitment the way I've described it, but you can generalize this to matrices. And then it sends over the decommitment D and the answer alpha. And the verifier checks, given everything that, the receiver, sorry, checks everything that it has received. And what we want is that if alpha is indeed the inner product of pi and q, then the verifier should accept. And on the other hand, if this is a lie, if alpha is not the inner product, then it should reject with high probability. So that's a linear map commitment. Actually, mention that the property that we actually use is not exactly binding. It's something called multi-extraction. I'll say a few words about this later. The other tool that we use is a linear PCP. So for some language L, we have a prover and a verifier. The prover generates some proof string pi, and it puts it in some box in the sky. The verifier samples some randomness R, generates a query. It can query this box and receive, by magic, the inner product between its query and pi. And then it decides whether to accept or reject based on that. And as usual for these proof systems, we want completeness and soundness. So if X is in the language, the verifier should accept. If X is not in the language, then no matter what the prover committed to in this box, the verifier should reject. So how are we going to put these two tools together? Pretty natural. One was a box. One needed a box. We're going to have the prover choose the PCP, generate the PCP string pi, commit to it. Then the verifier samples randomness for its query. The prover can compute the query by itself, and then opens this supposedly the inner product between the query and the proof pi, sends the verifier the decommitment and the answer. The verifier can also compute its query. Now it checks whether the verifier of the PCP would have accepted given the answer alpha, and whether the commitment was correct. Right, this is all super standard by now. And now this is interactive. We need to make it non-interactive. So what do? We just apply Fiat-Shamir. We're in the random oracle model. We're allowed to. So what does that mean? It just means that the prover generates the verifier's randomness by applying the random oracle to X into the commitment string, gets R. The verifier also has this as well. And now there's just one message. OK, great. Now, soundness of this. So completeness should be pretty obvious by construction. Soundness holds by the binding of the linear map commitment. So then this box actually, this commitment only allows you to do correct inner products. And if you can only do correct inner products, you're back to the soundness of the PCP. Great. This is, again, everything so far has been standard. But now let's look at the size of the proof. So what did we send? The prover sent a commitment string, the decommitment string, and the PCP query response. So I have to instantiate all of these. So for the linear map commitment, we're just going to take one from a known paper by Lai and Malavolta. They have a linear map commitment in the GGM where both the commitment size and the decommitment size are one G1 element. OK, that's great. So we have one G1 element for the commitment, one G1 element for the decommitment. But even in the best case scenario where the linear PCP was just one query, we still have one field element as a response from the linear PCP. So I promised you two group elements. So I need some new idea. And the idea is pretty simple, actually. It's just an observation that if the verifier somehow knows alpha in advance, it knows the query response in advance, we don't need to send it. And this leads to the question, are there linear PCPs where the verifier knows the response in advance? If there are, we can just plug that in, and we're done. And the answer is yes, kind of surprisingly. To me, it was surprising that we thought of this idea, and it just turns out that they exist. They're not normal PCPs, though. So the PCP that we use is one from BIOW, Barta, Ishai, Strovsky, Wu, I think. So they have a one query linear PCP for the NP-complete language gap MWSP. I will talk about all of this a little bit later. But for now, we just need to know that it has completeness error 1 over log n, soundness error 1 over n to the polylog n. And what we observe is that the verifier knows the response in advance in this PCP. So a few things to note. First of all, the completeness error here is pretty bad, 1 over log n. This is actually inherent for one-query linear PCPs. They showed this in this paper. We're going to have to deal with this somehow. Second thing to note is that this soundness error, if you want lambda bits of security for some security parameter lambda, this only gives you it when lambda is smaller than log to the c of n. I can kind of play around with the c realistically, but this doesn't give you like the entire parameter regime. So if you really, really want the entire parameter regime, then we also have an alternative PCP by, I don't remember the author names right now, where you don't have any condition on lambda. But you have to assume the unique games conjecture. And this is a conjecture basically about the existence of some NP reductions, some very optimal NP reductions. Just an interesting note is that this is kind of a conjecture for completeness and not for soundness. Like soundness holds, but we actually don't know like what the prover should do in some sense. It's kind of weird. But if you believe in the unique games conjecture, then there are PCPs where you even have the entire regime for security. Okay, so this is back to our picture. We were sending the commitment, the decommitment, and alpha. And now we got rid of alpha by predicting this independently. So verifier can just compute alpha by itself. Now the prover just doesn't need to send this. We had the minor issue that I mentioned before, that the PCP has really bad completeness error. So this SNARG will have really bad completeness error as well. And usually what we do when we want to amplify, we add a salt to the random oracle, right? And then the prover can add multiple salts to the random oracle, get multiple different Rs, and then choose the one where the verifier would actually accept. This is the honest prover. We can't do this here because we don't want to send any other bits. We've already sent 2 group elements, and we can't afford anything more. So instead, we use a cute thing, which is we kind of salt under the commitment. We notice that we're sending a commitment to some string pi, and if we commit to different strings, different vectors, then we should get a different commitment. This should re-randomize R, right? Because the random oracle is applied to this commitment. So we actually, instead of committing to pi, we commit to pi comma some salt I. So this is never actually sent to the verifier because the verifier's query is just not going to care about I, but it still is able to re-randomize this query. Yes, question?
Couldn't you just have the verifier just run through different I's as well, and until it finds something which accepts? Maybe up to some bound. So you don't send I, you just have the verifier plug in different I's into the random oracle.
You could do that. That would be less efficient for the verifier. Of course, that would work. But I think, okay, if I have to think about the efficiency here, because you get log n, you'd have to do quite a lot. Mm-hmm. And yeah, it might work. I don't know.
Just a side note. Yeah.
But it would definitely be less efficient. But yes, it might be. You might be right. I have to think about it. Okay, so let's do a very quick analysis. So we want lambda bits of security, and we're assuming that the adversary makes T random oracle queries. So before Fiat Shamir, the proof system has the error of the PCP plus the error of the binding error of the linear map commitment. The error of the PCP was roughly 1 over 2 to the lambda. The error of the linear map commitment, which we didn't see, is like t squared over the size of the group. This is all pretty standard. Now, if you apply Fiat-Shamir, you get t times this. So the first part is kind of fine, t over 2 to the lambda. But the t to the t cubed over the size of g is kind of bad, because in order to get lambda bits of security, we have to have the group be roughly 2 to the 3 lambda size. So instead of that, we also had to do some work to show that the Lima-Lavolta commitment has multi-extraction, which is a property that sort of plays better with Fiat-Shamir. And we show that it has multi-extraction error, roughly t squared over the size of g. And the point to note here is that the Fiat-Shamir with multi-extraction, you get t times the PCP error, but it doesn't multiply the multi-extraction error. So then you get t over 2 to the lambda plus t squared over the size of the group. So you're OK with a group of size 2 to the 2 lambda, which is now, this is standard. So overall, you get 2 G1 elements, which is roughly 4 lambda bits. And now I promised you that we will see something about this PCP, because it's a weird PCP. Well, I don't know if that's weird. The language is weird. So what is the language? The language is called GAP MWSP, GAP minimum weight solution problem. So you're given a matrix A, a vector B, and some integer D. And a yes instance it means that there exists some x, such that ax equals b. And also, x is quite sparse. So the Hamming weight of x is smaller than d. So in a no instance, so this is a gap problem, a no instance is that for every x such that ax equals b, the Hamming weight is quite large. So d times some polylog. And this is where the c is actually, somewhere in this polylog. So what is the PCP for this? The PCP is actually super simple. The prover just, so it has x, it has the witness. It just commits to x as the PCP, as the proof string. And the verifier is going to sample some random vector r and some sparse vector e, and we'll send as its query r transpose a plus e transpose. It's going to get as reply the inner product between these, which is, if you open it up, it's r transpose a times x plus e transpose x. And it just checks that whether a is equal to r transpose b. Really, for us, the point to note here is that this is known in advance. I know r transpose b. I don't have to, no one has to give it to me. I can just compute it. Which is exactly what we wanted. But just as some little bit of intuition here of what's going on in this PCP, well, we have two things that we want to check, right? We want to check that ax equals b, and we want to check that x has small Hamming weight. So this r checks that ax equals b, because if you hit it with a random vector, if this equality didn't hold, you would very likely not get equality later. So r transpose ax would not be r transpose b. So that's what this r part is doing. And this e part, the sparse e, is checking that x is sparse, because if x was not sparse, then you would very likely get something that's non-zero. So you sort of expect e transpose x to be equal to 0 if everything is actually sparse. This is also where the completeness error comes from, because this is not a very good test. Let's see how I'm on time. OK. So we're not really going to see this, because I don't have time. Before, maybe, if there are any questions specifically on the upper bound. OK. So about the lower bound, so remember we showed that there are no 1 G1 element SNARGs in the GGM plus ROM. I'm not going to get into, I have a few slides, but I'm not going to get into them. I will just mention the very high level proof idea. At a very high level, we first remove the random oracle queries by having the prover and the verifier simulate the random oracle sort of independently, either independently or in the CRS. We have some cases that we have to treat. And then once we've removed the ROM queries, we're basically in the Groth16 world where there's just a one group element SNARG in the GGM. So really, the challenge is to remove the ROM queries. And I will skip these. This talk, I showed our main results was the two group element SNARG and the GGM plus ROM, and we have also a limitation that you can't get one group element SNARG in the same model. So what are the open problems here? So I mentioned at the beginning that this is not practical. And I want to say kind of why. The main bottleneck actually comes in this gap MWSP problem. So it is NP complete. There's a proof of NP completeness. But the proof of NP completeness is quite complicated. It goes through the PCP theorem. It's extremely inefficient. So if you want to actually use this, you would want to take your R1CS instance, something like that, and reduce it to gap MWSP, and then use that. But this reduction is extremely inefficient right now. It very likely there is a more efficient reduction. We didn't really look into this, but this would be probably the main thing where if we improve that, then we would get a actually practically efficient SNARG. So either improve this NP reduction or just build a linear PCP for a language that's kind of more natural, but that has this property that you can predict the response in advance. Also, we would want pre-processing. So right, this is a SNARG for a universal language, which inherently means that the verifier is going to need to work in at least linear time because it needs to read the circuit that we're talking about. So what we usually do in this world is do some pre-processing in advance, and then somehow the verifier can work in much less time in the sort of once it gets the proof. It's not really clear how to do that here with this kind of PCP, but it might be, it's very likely to be possible, and then you would get a more efficient verifier as well. Another open problem is notice that our lower bound only shows that you can't have one G1 element in the GGM plus ROM, but maybe one G1 element plus one field element or some bits that might not encode a field element necessarily. That's not ruled out by our lower bound, and it might still be possible. It would be very, very interesting if someone can get something like this. That's it. Thank you.
Other questions?
Yeah.
Roberto.
Thanks for the talk. Can I ask about the verifier computation? How much it is? Because it seems it's like as big as the witness, right? It's not succinct.
Yeah, the verifier computation is not succinct because this, at least using it naturally, this linear map commitment that we're using requires the verifier to work in linear time in the size of the PCP, or so basically the witness.
Thanks.
Yeah.
More questions? There are
designated verifiers SNARGs with one group element.
Yes. So this was all in the yeah. There.
maybe
So guys,
the
if you're asking questions, please use the microphone because then the streaming could hear you as well.
Yeah. So where does the proof not apply to designated verifier SNARGs?
In the designated part, and the fact. So we're relying on right even like Roth 16, the lower bound, it relies on the GGM. It relies on not being, all sides sort of not knowing the discrete logs of things that are in the CRS. But that's just not true in the designated verify setting.
Got it.
Okay, maybe while the next speaker sets up, I was wondering, so for Groth 16, we know that we can also prove it in the algebraic group model. Have you any conjectures of whether you could transfer
This should be provable in the, there's nothing that special going on here. I think, or do you mean the lower bound? Sorry.
No,
the upper bound.
result.
The upper bound should work in the algebraic group model. Yeah.
Okay. Yeah, I guess for the lower bound it follows. Okay, then let's thank the speaker again.
Thank you.
So next we have